Good afternoon, everybody. Welcome to Wednesday afternoon of Organic Chemistry, Chem 170, with your host, me, Dr. White. Hi. All right, a couple things I have to talk about. First of all, we're back on track, which is a good thing. And what that means is a week from today will be test number two. Test number two. And test number two will cover alcohols, thiols, epoxides, ethers, ketones, and aldehydes. Wow, that's a lot, but that's always test number two. Now, between now and Saturday, I will post on D2L. I almost said this uh, computer system for the wrong school, COD, but I got it right, D2L. But I can tell you this, I forgot how many pages there are on problems, but it will cover nomenclature, about 40 points, 39, 40 points. And nomenclature means here's the structure, give the IUPAC name, or here's the name, both common or IUPAC, draw the structure. Next, I'll have about 60 points on reactions. And most of those will be give the product or products for the following reaction. But it will have, I think, 3 or 4, I forgot, synthesis problems. What I mean by that is give the starting material or starting materials, otherwise known as reactants, but I come from industry and we call that, the chemical industry, we call that starting materials for these reactions. And hang in there one sec. And there'll be about, I don't know, 8 or 9 points, whatever, about on general knowledge. Now, if you add it all up, are you ready for this? There's going to be five bonus points. So that'll help you out. And with that, before I do that, I haven't done this in a while. Did anybody think about when you drive by a gas station, that gasoline contains an alcohol, ethanol? Did anybody pick up a bottle of rubbing alcohol, which contains mostly isopropyl alcohol? That's an alcohol. Did you pick up a bottle of nail polish remover and see it contains acetone, which is a ketone? You should know these things. And finally, something dear and dear to my heart, did you have some vodka? Let's call it Polish vodka, not Russian, or American vodka, or French vodka is good too. And that contains ethanol, or we can get closer to home. Did you have any Canadian Club, which contains ethanol, and that's an alcohol? And these are things you should think about, because guess what? Organic chemistry is all around you. I stole that from SpongeBob, and it won't hurt you to think about it. Trust me, I'm a chemist. Trust me, I'm an organic chemist. How about this one? Trust me, I'm a doctor. Do any of those work? Think about organic chemistry. All right, today's game plan. We're going to go through the ether epoxide problem set. We will finish up the ketone aldehyde chapter. And because of that, next Monday, I will go through the ketone aldehyde problem set here in class and lecture. Also next Monday, I will give my world famous review for next test, test number 2, which will be a week from today. And we'll do test number 2 just like I did test number 1. At the end of the day, after our lecture and lab, I will email out eel. Oh, I do like eel. But anyways, I had a lot in the other ones. But anyways, I will email out the password for the password protected PDF file that next Tuesday you'll be able to download from D2L. And you'll have until the next day to log in or upload your answers. And again, if you don't have a printer, you don't have to write out all the answers. I mean, let's try it again. Hold on, I got to reboot my brain. There, you don't have to write out all the questions, just the answers. If you don't have a scanner, you can use your cell phone, take pictures. I have, like you've been doing for the labs, a file that tells you how to do that. All right, let's get going. We have been going. All right, everybody should see ether and epoxide practice problems. Can you guys keep a secret? Do you notice there's no nomenclature questions on there? Because I don't think I've ever put an ether nomenclature question, and I didn't teach you epoxides on the test. So you don't have to know that, but yeah, I did teach it to you. All right, let's go through some reactions. Question is, give the organic product or products for the following 3 points each. And how do you do that? Let's look at A, and you look at an organic molecule. I've been training you to do that. Look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention like that. And the first one we have, and I didn't ask you to learn the name, but I'll use it because I do know it, an alkoxide. Notice oxygen minus, sodium plus, cation, and the oxygen minus is attached to an R group, in this case 1 carbon, alkoxide. Second molecule, carbon, ooh, halogen, alkyl halide. I don't have here, I should have, bad Dr. White, but X can be chlorine, bromine, or iodide. And what happens is the oxygen, O minus, attacks, organic chemists are violent, and bonds to the carbon with the halogen, and kicks out the halogen, and you get a salt plus an ether. And here, notice R is methyl, R prime is N-propyl. Notice the halogen is on the N carbon, therefore the oxygen is bonded to the N carbon of 3 carbons. Now in B, same thing, oxygen, O minus on an R group, this case is cyclopentane ring, and a sodium cation, carbon with a halogen, alkyl halide, the same reaction. And this oxygen bonds to the carbon with the halogen, which leaves, and you get this ether. Notice, and this is important, that oxygen is bonded to the center carbon because that's the carbon that had the halogen. If you bond it to the end one, I'm going to mark it totally wrong because it is. So you have to be careful. Now something, I'm going to let you have some fun. And the question would be, what's the organic product or products for the following reaction? 3 points each. right, I think everybody's done. So let me get to work. How do you do this problem? And remember, these problems are how organic chemists make molecules. And these are like what a, say, carpenter uses, a 2x4, plywood, nails, screws to build things. Well, organic chemists use these general reactions to build molecules that you use in your daily life. Now, my examples usually don't have that, but they can. All right, what's different in the first molecule here? What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond? Ooh, oxygen minus sodium cation on carbons, and that's an alkoxide. And second one, carbon with a halogen, alkyl halide. This is my R group. This is my R prime. And when you react the two together, what do you get? An ether plus salt. Now, this is inorganic. So if I ask for the organic products, you don't have to write that down, but if it helps you, feel free to. Now, this attacks and bonds to the carbon with the halogen, and it kicks out the halogen. And do you break carbon-carbon single bonds? No. So you have 1, 2, 3, 4, 5, 6 across. And this carbon is this carbon. And that's my R prime, bond to oxygen. And what's my R group? 2 carbons. And you know there are 4 bonds to carbon. And that's how you make that ether. Now, the next reaction I'd like to talk about is D. And D, you have what's different? Carbon-carbon, hydroxyl group on a carbon, alcohol. And the second molecule, 3-membered ring, 2 carbons, and oxygen, ethylene oxide. And I'll never ask you on a test what's the name of ethylene oxide or draw it, but I will use it in class, and I have. And when you react an alcohol with ethylene oxide, it pops open this 3-membered ring to make this ether alcohol. And what's our 4 carbons? Carbon with the hydroxyl group will be the carbon on the oxygen here of the ether. And there you go. And the one I just had you made in D is a molecule they actually sell for the key ingredient in oven cleaning compound or product, the cold one, not the hot. Now, in E, I did the chemistry instructor's favorite trick on a test, put a big, scary molecule. But if you know what to look for, it's not big, it's not scary, it's just a molecule. And what's different? What's not carbon? What's not hydrogen? Hydroxyl group on a carbon, alcohol. My R group is a 5-membered ring with 2 methyl groups on it, and also has the alcohol. Ethylene oxide, same reaction right here. And I get my R group because you don't break carbon-carbon single bonds. And then O, CH2, CH2, OH. Now, let's look at G. Now, G, I have a benzene ring and a hydroxyl group on that, but this is ethylene oxide. 9 means 9 moles or 9 molecules. That will not react with a benzene ring on its own, but it will react with an alcohol, and a benzene ring is my R group. And when you have N, that's why I have a number in front is not the number one, and that's called the coefficient. When the coefficient is 2 or greater, the following reaction, alcohol and moles of ethylene oxide, you get this polyether alcohol. Poly means many, ether right here. And I showed you how this is formed. In this case, N is 9. And R is benzene ring, bracket, O, CH2, CH2, close bracket, what's N? 9. And then the hydroxyl group on the outside. Now, listen carefully. Common mistake on test number 2 is people, meaning students, put the hydroxyl group inside the bracket, and that doesn't exist anywhere, that molecule. It can't exist, and therefore I mark it wrong. So remember, for this reaction, the hydroxyl group is outside the bracket with the subscript N. And here for H, I gave you 1, 2, 3, 4 carbons, alcohol, reacting with 5 moles or molecules, ethylene oxide. Same reaction up here. You get this polyether alcohol, R, 4 carbons. Then my bracket, OCH2, CH2, close bracket, N is 5, and OH. All right, let's look at, because there are going to be 3 or 4 synthesis problems, which is really the fun part of organic chemistry. And let's look at number 2A. And there we have 2 things, and that's what the question marks are. When I was a student, my instructor didn't put question marks down, but if it's more than one starting material or product, I'll help you a little. And what are we making? We react 2 things to make this compound plus the second, NABR. And what's the functional group in the product that's organic? Oxygen with carbons here and here, and ether. And this is a salt. X can be chlorine, bromine, or iodide. In this case, it's bromine. And how do you make an ether? The Williamson ether synthesis. RO minus Na plus alkyl halide R prime X. Now, if I take and say the methyl is R and the ethyl is R prime, then you would have the chemicals on top. If I did the opposite and said the ethyl is R, and you would have this alkoxide, and the methyl is R prime, and notice in both cases, the halogen you're given right here in NaX is a bromine, and that's how you do it. Now, everybody look at C. Cross that off. I said I wouldn't give any synthesis with epoxide. I got carried away and forgot that, and C will never be on a test as a synthesis problem. Speaking about synthesis problems, why don't you try one? What would be the 2 starting materials I react together to make those 2 compounds? Ooh, that would be maybe even 6 points or 4. If I have chance and time, and I think I should, at the end of today's lecture and lab, I'll tell my Mardi Gras story. Yes, I've been to Mardi Gras a number of times in New Orleans. I heard they really know how to party hard in Brazil, at least when there's no pandemic. All right, I think everybody's done. So let's get moving forward. How do you do one of these problems? How do you figure out what are the two starting materials? You look at the products and you look for what's different. Ooh, oxygen. Remember, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. So I have carbons here, oxygen, and carbons here. They're different. That's an ether. And I also have a salt. And here X can be, and it is chlorine, but it could have been bromine or iodine. I don't know if I've ever mentioned to you, if you ever go out to lunch, breakfast, or dinner with a bunch of chemists, especially organic chemists, and someone wants the salt, they'll ask, can you please pass the NaCl? Everybody see that? NaCl. I've been guilty of that many times myself. All right, so how do we do this? We say, I'm going to call this methyl R and this isopropyl R prime. If that's the case, R, oh, by the way, how do you make an ether? Alkoxide plus an alkyl halide. So R is methyl, and you get this alkoxide. You don't have to show the charges, but I always do because I think it just looks cool. Dr. White's always trying to be a cool dude, especially with chemistry. R prime, remember the carbon with the oxygen bond to it will be the carbon with the halogen. So I have 3 carbons. Oops. Didn't want to do that. And my halogen is chlorine. And I know there are 4 bonds to carbon, so I can put it into hydrogens. Now, what if I did something different? I said, no, I'm going to call this R prime and this R. In that case, my R group is isopropyl. The carbon with the oxygen here is the carbon with the O minus in the alkoxide here. And my R group, R prime, is now methyl. And my halogen is still chlorine. So which one of those are correct? Both are. And I would know, but you wouldn't. The bottom one in blue, the chemicals cost less, so your direct cost is what they say. The chemical industry would be the better one, which would maximize your profits, would be in blue. But for my test, both are correct. And that's how you do it. Any questions about ethers and epoxides? I guess not. You know something? I like when people with beards can do this, look very authoritarian. But anyways, you know something? I think you need a pick-me-up, something to pick me up. And I have just the thing. It's time to play the fun game Circle and name the functional group. 2 points each. How do you play that fun game? Circle and name the functional group. 2 points each. Well, let's have fun. Let me get a larger part. All right. Whoops, I don't want to do it in that color. And some of them might have more than one. Oh, I'm going to let you have a lot of fun today. Oh, let's do one more for you to work on. And there you go. Circle and name the functional group. 2 points each in the following molecules. I'm not asking you to give the IUPAC name. Just circle and name the functional groups. 2 points each. And I'll give you some time to work on that now. One of these days while I'm doing a problem like this, I'll play game show music, like The Price is Right, which I have watched in decades, or the other ones, how they have the big question at the end, and the music goes dun, 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 and I better not sing it. It'll ruin your day. It'll ruin my day too. And I'm giving you extra time because this one takes a while to finish. All right, I think everybody's finished. So let's play circle and name the functional group, 2 points each. And how do you play that game? You look at an organic molecule and what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention like that. Let me turn on my video. I'm back and never was gone. And if we look here, an oxygen with carbons there and there, this part you don't have to do, I will. Whoops. And that's an ether. And if we look at B, what's different? Ooh, oxygen with a hydrogen and a carbon. And you don't have to write this, but I will. But that's an alcohol. And don't forget, next time you drive by a gas station, don't forget, up to 10% of gasoline, of the weight of the gasoline contains ethanol, another alcohol. And you could just circle that. If you circle a little more, that's okay. Let's look at C. What's different? Ooh, oxygen double bond to carbon with a hydrogen and carbons. And what is that? That's an aldehyde. And let's go to D. What's different? Ooh, oxygen double bond to carbon. Notice there are carbons here and carbons here, and they're connected together. This is a ketone. It's cyclic, so R and R prime are connected, but and remember, ketone is not spelled with a Y in there, even though that's how you pronounce it, ketone. In fact, a number of years ago, I haven't been Halogen in about at ECC, coming up in about 6 weeks. It's been 2 years since I've been on campus physically. I've been there on D2L, on Zoom. But anyways, there used to be a company, automotive company, parts company. I'd see their truck and it was Ketone Auto Parts. I think they had a Y in their name though. And finally, we have E. I think I threw everything in E except the kitchen sink. And if we look, what's different? Ooh, hydroxy group on a carbon. Alcohol. Ooh, carbon double bonded oxygen. Carbons here, that's a carbon. Carbons here. That's a ketone. Then, ooh, another oxygen here, double bonded carbon here, carbons here, carbons here. That also is a ketone. And just so happens R and R prime are connected together in the ring. Now if we come over here, ooh, an oxygen, carbons here and here. What's this? It's an ether. Oh, we're not done. Another oxygen. And notice we have carbonyl, carbon double bond oxygen, hydrogen, carbons right here. And what is that? That's an aldehyde. And that's how you play that fun game. Circle and name the functional group, 2 points each. Now, it is a fun game, but on a serious mode, if you're doing organic chemistry and you can't identify the functional group in a molecule, you can't name it. If you are doing organic chemistry and you don't realize what functional group is in a molecule, how are you going to know how to react it? You can't. And that's why it's important to play that fun game, circle and name the functional groups, 2 points each. I hope you all enjoyed it. Any questions about that? All right, well, in that case, let's get back to ketones and aldehydes. On Monday, I was talking about something very, very important to me personally as an organic chemist. And that's the Grignard reaction, which I haven't talked about yet, but I was talking about the formation of the Grignard reagent. And that's named after the great French organic chemist who won the Nobel Prize for this in chemistry for this work, Victor Grignard. And if you take an alkyl halide, where X can be chlorine bromine iodide, react it with magnesium metal, you do this in ether. Ether is a very good solvent for a lot of reactions. And what you get is the Grignard reagent. And why don't you try this one? What would be the product or products, organic product or products for the following reaction? 3 points each. And I have made Grignard reagents and I've used them too. Oh, it's so nice and very important. And you'll see why in a little while. All right, I think everybody's done. Let's look at this. What's different? What's not carbon? What's not? Ooh, a halogen on a carbon. Alkyl halide. Remember, X can be chlorine, bromine, or iodine. In this case, it's chlorine, plus magnesium metal, and you form the Grignard reagent. And here, what's our R group? This. Do you break carbon-carbon single bonds? No. So I start with 4. I better end up with 4. The carbon with the halogen will have the Grignard. Remember, the order is important. It's the magnesium, and bond to the magnesium is the halogen, in this case, chlorine. This counts as 1 bond, so I can put in hydrogens, because I know there are 4 bonds to carbon. And that's how you get the Grignard reagent. Oh, let's have some real fun with this. what would you react with magnesium to make that compound? Your turn. You believe we're already in week 6 of this semester? Wow. Time flies when you're having fun with ketones and aldehydes and other stuff. And I think everybody's done. So I'm going to get to work. And how do we do this problem? How do we figure out what do we react with magnesium metal to make this compound? What's different? What's not carbon? What's not? Magnesium iodine on a carbon. And that's a Grignard. Remember, X can be chlorine, bromine, or in this case, it is iodine. And how do you make a Grignard reagent? An alkyl halide plus magnesium. Now, the carbon that this is bonded to is the carbon that the halogen is on. Therefore, what's my R group? 4 carbons, T-butyl group. And then attached to that would be the halogen, in this case, iodine. And I know there are 4 bonds to carbon, so I can put in the rest of those. And I actually made this Grignard in grad school. I remember it, except instead of iodine, I think I had chloride. And the question is, why are you all getting excited about the Grignard reaction or Grignard reagent? And that's because it allows you to do something that's very rare and very wonderful in organic chemistry. What's that? Well, let's find out. And this is one of the reasons Victor Grignard won the Nobel Prize. Now, once you make the Grignard reagent, you can react it with an aldehyde and ketone with this reaction. Let me write it on the whiteboard, but before I do that, I need to teach you a convention that organic chemists use all the time. Say you react 2 things, A and B, and they make something. And then after that happens, whatever you made, you react it with whatever this is, say C, to make a product D. Well, what organic chemists do, because we're lazy, instead of writing this all like that, we do the following. And what this says is A, first step reacts with B, and then in the second step, it reacts with C, and if I were to write, and it makes D. So that's a very easy way of writing a 2-step reaction in a condensed, lazy way. And organic chemists are lazy. Let's look at the Grignard reaction. Now, if R prime is a hydrogen, it's an aldehyde. If R prime is carbons, it's a ketone. I use a triple prime now. And the first step, you react it with a Grignard. And the second step, you add acid, H plus, and water. Now I'm going to do something I rarely do, and this will never be on test, is show you a mechanism. Mechanism is a step-by-step way these things undergo a reaction. Now remember, the carbonyl of a ketone and aldehyde is polarized slightly. The carbonyl carbon is slightly positive, the oxygen is slightly negative. And think of the Grignard, not actually, but think of it as R triple prime plus and MgX minus. And a carbon with a plus charge is not happy. It's, oops, I did that wrong. It happens once in a while. R minus MgX plus. Sorry about that. And think of this carbon with a minus charge as unhappy. What does it want? Where can I find positive charge? At the carbonyl carbon. And this attacks that carbonyl carbon. And it opens it up to this. Because these electrons go here. And now this actually is our O minus MgX plus. And the first step was reacting it here with the Grignard. The second step is reacting it with acid and water. And what this is, whole thing is called the conjugate base of an acid, in this case, an alcohol. It's a strong base. And you add an acid, I'll put a proton on here, and I'll get back the alcohol. Remember, R prime could be hydrogen. And what's so special about this? Well, look what we just did. We made a carbon-carbon single bond. The carbon with the Grignard is now the carbon in R triple prime attached to this carbon that used to be the carbonyl carbon. And that's very special, very rare in organic chemistry. And Dr. White got carried away. I wanted to finish this part. And I went a whole minute into our break. Oh no, I'm sorry. But anyways, come back at 1:56 and we'll continue on with this amazing reaction. Come back in 5. oops, I went an extra 30 seconds late. Let's get going. All right, we're talking about, or I was talking about, notice I say we, I was talking about, it's imperial we. I was talking about, well, I've got my royal blue on. But anyways, I was talking about the Grignard reaction. And this is where you react the ketone and aldehyde to make a carbon-carbon single bond by reacting with the Grignard reagent. And so the overall reaction is this. Whoops, wrong color. Right color. Ketone or aldehyde, when R prime is hydrogen, it's an aldehyde. When R prime is carbon, it's a ketone. And then you react it with a Grignard. Remember, X can be chlorine, bromine, or iodine. And in the second step, acid and water. Keep your eye on the carbonyl carbon, carbon double bond to oxygen. That's where the fun is. Oh, really? And what's attached to it, R prime or hydrogen, R double prime is still there. And from the Grignard, you make that very special thing, a carbon-carbon single bond to another carbon. And this opens up this carbon to an alcohol. And that's one of those special times you can make a carbon-carbon single bond. So let's have fun with the Grignard reaction. And in my PhD thesis, I use this a lot and similar reactions too. And I won't cover it today or this whole semester. And let's look at this reaction. And if we look at what we're starting with, what's different, carbonyl with a hydrogen and carbon, that's an aldehyde. Now, it could have been a ketone, but in this case, R prime is hydrogen. R double prime is a methyl group. This is R prime. And then if we look up here, what's different, carbon, carbon, ooh, magnesium iodide. This is a Grignard reagent. Second step, acid and water. And this attacks that, forms a special thing, a carbon-carbon single bond. What was on the carbonyl carbon is still on there. It opens up to an alcohol, and you make that very special thing, a carbon-carbon single bond. Now, what's our triple prime? 3 carbons. So I have my carbon here, carbonyl carbon, which is this carbon. R prime is hydrogen, R double prime methyl. The carbon with the Grignard is the carbon in R prime attached to this carbon right here. And you don't break carbon-carbon single bonds, so our triple prime, 3 carbons. And in one step, I took 2 simple molecules, I made a more complex molecule. And Dr. White's really happy. It's fun to do that, even on paper. And that's the Grignard reaction.
Dr. White, can you please scroll up a little bit?
Is that better?
Thank you.
Remember, I warned you I got the fastest mouse wheel finger this side or the other side of the Mississippi. How many of you have ever seen the Mississippi? Beautiful river. I've flown over it many times. I think only once I saw it from the ground. Back in the 80s and 90s, wow, that was a while ago. I used to have to go to California a lot. So from Chicago, you'd go over to Mississippi. If you had a good pilot, he'd tell you about it. I always had a window seat. No, I had an aisle seat too. All right, let's finish. Let me give you the rest of this. And there you go. Give the organic product or products for the following reaction. Now we're getting into good stuff. Well, the other stuff was good too, but this is excitingly good. Is that a phrase? Well, I just invented something new. Excitingly good. I guess as opposed to excitingly bad, yuck. Oh, warning, it's Bad Humor Wednesday. We all have to suffer now. It's excitingly good, almost like an oxymoron. All right, let's get going. If we look at this molecule, we're starting with what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Ooh, oxygen, double bond to carbon, carbons here and here. That's a ketone. Now, it could have been an aldehyde, but it's not. And what am I reacting at first? Carbon, carbon, magnesium halide, bromide. That's a Grignard reagent. Remember, X can be chlorine, bromine, or iodine. And second step acid, H plus and water. And what happens? This attacks and bonds to the carbonyl carbon. What's attached to it stays attached. Opens it up to an alcohol, and you do that special thing. You make a carbon-carbon single bond from the Grignard to the carbon that was the carbonyl carbon. So what's our prime? Methyl. What's our double prime? Ethyl. And what's our triple prime? That's also ethyl. So what's attached to my carbonyl carbon? R prime methyl. And also our double prime ethyl. I open it up to an alcohol, and now I make that special carbon-carbon single bond. And look at, from simple molecules, you now have a very complex alcohol. In fact, I don't know an easy way to make that without using the Grignard reagent. I don't even think I could, it would be very hard for me to come up with a synthesis to make that easily like this without using the Grignard. Oh, let's do another one because this is fun. Now you know I'm an organic chemist. And there you go. Now, while you're working on that, it's time for a slight little present from Dr. White. Remember, little present, and that is on my test number 2, and also on the final, I will never give a synthesis problem involving a Grignard reaction. Like this. It's just not fair to you people. At my level, yeah, I can do that, but I'm not expecting you to do a synthesis, but I do expect you to know how to react it. I can still picture in my mind in grad school running the reactions like this. It was fun. Now, for those who are having a little difficulty, let me give you a little help. Little, but it should be helpful. All right, I think everybody's done. So let's take a look at this. What's different in this molecule? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Ooh, oxygen double bond to carbons with carbons here and here in the ring. That's a ketone. Now in a ring, our prime and our double prime are connected together. And what am I reacting it with? One carbon, magnesium halide. It's a Grignard reagent. Remember, X can be chlorine, which it is, but it could have been bromine or iodine. Second step, acid plus water. And what does it do? This attacks the carbonyl carbon and forms that very special thing, a carbon-carbon single bond. And what's attached to that carbon is still attached, our prime or H and our double prime, and it opens up to an alcohol, and you make that very special thing, a carbon-carbon single bond between our triple prime and what was the carbonyl carbon. Now, do you break carbon-carbon single bonds? No. So I still have what's attached to this carbon attached to it. This attacks that, opens it up to an OH group, and my R triple prime is methyl. Now, if you wrote the hydroxy group OH on top and the methyl on the right here, had these reversed, that's right for this class. So That's the Grignard reagent. And it's a wonderful reaction because it allows you to do something very special, very rare, make a carbon-carbon single bond. All the hundreds of reactions I know, there's only a handful, about 20, 25, that I'm not going to teach you all of them, but I know them because I've used a lot of them, that allow you to make a carbon-carbon single bond. Very rare, very special. All right, let's move on. Now, if you look at a carbonyl, and here, this could be a H, so aldehyde or ketone. This carbon oxygen double bond is a pi bond and a sigma bond. And you learn from double bonds, if you add a hydrogen and a catalyst, guess what? You will break the pi bond and each atom of the double bond will get a hydrogen. And this is called halogenation, also sometimes called reduction of a ketone or aldehyde. And just like you learn for double and triple bonds, the same catalysts are used, nickel, platinum, or palladium. And you break the pi bond, and each atom of the double bond, carbon, oxygen, gets a hydrogen. That's another way of making alcohols. So let's take a look at this reaction. And the question is, give the organic products for the following. If we look at this, what do we have? What's different? What's not carbon? What's not hydrogen? Ooh, carbonyl. Carbons here and here. That's a ketone. It could have been an aldehyde, but it's not. And we're reacting with hydrogen gas, H2. And what's nickel? It's a catalyst, which I'll abbreviate like that. And the catalyst could be nickel, platinum, or palladium. You break the pi bond right there. What's attached to the carbons are prime or hydrogen. Our double prime are still there. And there you go. So in this case, what's our prime? Methyl. Our double prime? Methyl. Here's my carbonyl carbon. It's this carbon right here. What's attached to it? Whoops, wrong thing. I have, oh, where did I go? Sorry about that. Our prime is methyl. Our double prime is methyl. Break the pi bond and each atom, and you make the expensive way of making isopropyl alcohol from acetone. So if you're ever on a desert island and you have plenty of nail polish remover, acetone, you have hydrogen nickel catalyst, you can make isopropyl alcohol, make your own rubbing alcohol. But you never thought of that. All right, your turn to have some fun. And there you go. Have fun. All right, I think everybody's done. Let's look at this reaction and we look for what's different. And by the next couple of weeks, you should start having nightmares hearing me say, look for what's different. But it's always true. When I look at an organic molecule, I scan it, look, look, look. I look for what's different because that's where all the action is and fun. All right, what's different? What's not a carbon? What's not a hydrogen? Ooh, oxygen double bond to carbon, hydrogen carbons. This is an aldehyde. Now, it could have been a ketone, but it's not. And we're reacting it with hydrogen, and platinum right here is a catalyst. Remember, your catalyst can be nickel, in our case, platinum, or palladium. And you break the pi bond. What's attached to that carbon is still attached, our prime or hydrogen, and our double prime, and you make an alcohol. And this is sometimes called a reduction of aldehydes and ketones. So what's my R prime? Hydrogen. What's my R double prime? 1, 2, 3, 4 carbons. Here's this carbon. It has R prime attached to it, R double prime and R prime, and you break the pi bond and you form this alcohol. And that's how you do it. Oh, let's do one more. Here's one more for you to have fun. Am I sharing today or am I sharing? Don't answer that. I think the word got out to some people throughout the United States that my videos for organic are available on YouTube. Because if you look, I think there's 15 people in the class. but my YouTube videos this semester have been getting like 35, 40 views. Well, some of you are coming back multiple times and enjoying Dr. White on YouTube. All right, let's move on. Let me do this. If we look at this molecule, we'll look for what's different. And, ooh, oxygen, double bond to carbon. Carbon's here and here. And we have a ketone, cyclic ketone. Remember, in a cyclic ketone, it could have been aldehyde. It's not. This is connected. And if we react it with hydrogen and a catalyst, in this case, the catalyst is palladium, but it could have been nickel, platinum, or like I said, we're using palladium. And you break the pi bond, and each atom of the double bond gets a hydrogen. And what's attached to this carbon here is still attached there. So my whole ring, think of our double prime and our prime. Since you don't break carbon-carbon single bonds, I'll redraw it with the methyl groups. And this carbon here, right there, is this carbon, which becomes this carbon. And what do we see? That has an alcohol. And that's how you do it. All right, let's continue on. Now, let's look back at this reaction right here. And if you had an R prime, double prime or prime, a double bond, and you didn't want to lose it, but as soon as you reacted with hydrogen and catalyst, you would lose it. Because you learned this for test number 1. So what happens if you just want to do this reaction, but not this one? Well, it turned out problems like that exist in organic chemistry. And during World War II, a great organic chemist from the University of Purdue, Dr. H.C. Brown, and came up with a new reagent. And this allowed you to react a ketone or aldehyde and do the same reaction I just said, but this new reagent will not react with carbon-carbon single bonds. It only reacts with carbon-oxygen double bonds, I should say, will not react with carbon-carbon double bonds. And that new reagent is lithium aluminum hydride, otherwise known as LiAlH4. And think of lithium aluminum hydride like H-. And similar to Grignard, which was like R-, this will attack the carbonyl carbon, open it up, and second step, add acid and water to make an alcohol. It's essentially the same reaction we just did, except this reagent will not touch a carbon-carbon double bond, which is a good thing. And the question is, give the organic product for the following. And if we look at the starting material here, what's different? What's not carbon? What's not hydrogen? Ooh, oxygen double bond to carbon. Carbon's here, R prime. Carbon's here. And we have a ketone. Now you could have had a aldehyde, but we don't. And when you react it with lithium, excuse me, aluminum hydride, second step, acid and water, what's attached to this carbon? Is still attached. And just like the last reaction I showed you, you break the pi bond and each atom of the carbon oxygen double bond gets a hydrogen. This is R prime. This is R double prime. And here, what's attached to carbonyl carbon here still is there, R prime, R double prime, and this opens up to an alcohol. And that's how you do it. And the beauty of this is this will not react with a carbon-carbon double bond, where hydrogen catalyst showed you before will react with that along with the carbonyl carbon oxygen double bond. And there's one for you to have fun with. All right, let's do this. What's different? What's not carbon? What's not? Oh, oxygen, double bond to carbon, carbonyl. Carbon's here. Carbon's here. It's a ketone. Could have been an aldehyde. And I'm reacting with lithium aluminum hydride. It's really fun stuff to work with. I have done it numerous times, a long time ago, when I worked on a bench. What's attached to carbonyl carbon is still there. And you break the pi bond, and each carbon, each atom of double bond gets a hydrogen. Here's my carbonyl or carbon. That's this carbon. What's attached to it? R prime. You don't break carbon-carbon single bonds. R double prime, 3 carbons. And this becomes an alcohol. Now, the previous reaction I didn't give you, but I can on a test, but I'll do one now, and that's the synthesis problem. And the question is, what do you react with lithium aluminum hydride to make that molecule? And second step's water. And while you're doing that, time for a commercial from Dr. White. Don't forget tonight from 5 to 6:15, I'll have my office hours. If you have any questions, stop by. And it's located on your local neighborhood Zoom channel for Chem 170 office hours. It's in the syllabus. And also on the front page, D2L, there's a link there. If you look, have been outside this afternoon or late morning, you know, spring is not far away. Ooh, excuse me. Even though I hate to say this, back when I was junior in college, that was 1967. Oops. On April 14th, the day before taxes were due here in Chicagoland, we got 14 inches of snow overnight. And the reason I remember that is because the next day it all melted because it warmed up. We had real mess in Chicago land area. And that's the only time in my lifetime in the Chicagoland area, because of that problem with the snow and it melting, they extended the deadline for taxes by 1 day. So in Chicagoland, we can still get snow in the middle of April. Hope not. All right, let's do this. We look at this molecule. First of all, I'm using lithium aluminum hydride. And for this class, and most of the time, like almost always, you're going to get an alcohol. And one way to think of an alcohol with lithium aluminum hydride is this way. And one of these hydrogens is R prime, and this is my R double prime. And what do you start with? And like I said, there'll be 3 or 4 synthesis problems. And if I said it won't be on the test, like a Grignard, it won't be, or ethylene oxide reactions, but everything else is fair game for synthesis, like this reaction. So this carbon here, which is this carbon here, becomes that carbon, which if I end up with 3 carbons, I better start with 3 carbons. And this carbon has a double bond to oxygen, hydrogen, which is R prime, and 2 carbons, which is R double prime. If you take this and do the reaction, you will get that. And that's how you do a synthesis problem. Oh, hold on. Sorry about that. All right. Let me get stuff so you can see. All right, everybody see oxidation of carbonyl compounds? That will not be on test number 2. It will be on test number 3. So right now, put an X through it, like there you go. And let's move on to the next slide. All right, I have to warn you about something. Next couple of slides, first of all, I'm going to turn the switch. Will this be on test? Click to the off position. But this is a background for a reaction that will be on the test. And I should tell you, if I'm having way too much fun, that's because this is an area I'm a world authority in. I did my PhD thesis, and my last and first patents worked with some of this stuff. All right, now aldehydes and ketones exist in an equilibrium in 2 forms, and those are called the ketol and enol forms. And again, switches off. Now I'm going to show you a special type of aldehyde or ketone, and I'll draw it this way. And something I won't ask on a test, but you should be familiar with is the carbon attached to the carbonyl carbon is called the alpha carbon. This is the alpha carbon. If you take a hydrogen over here and move the bonds over here, there's an equilibrium that exists. Like this. And this is called the keto because it's like a ketone. And ene double bond alcohol OL. And this is called the enol form. And this exists in equilibrium, which makes aldehydes and ketones very special. And what makes it special? Because of the following. The hydrogen, alpha hydrogen, the hydrogen on the alpha carbon in a carbonyl compound is more acidic than the hydrogen on an alkane of a carbon atom. And this is due to resonance stability and the formation of the enolate anion. Smile when you say that, because my PhD thesis and my first patent and my last patent dealt with enolate anions. What I could do, nobody else could. And I love enolate anions. So does Mother Nature. So if we look at this, and here I have the alpha carbon, and these hydrogens, again, switches off, are acidic. And what does that mean? There's an equilibrium where in an acid-base equilibrium, you lose a proton off the alpha carbon. And why does this happen with ketones and aldehydes and not alkanes? Because I can draw a resonance form, move electrons there and there. And I use a double-headed arrow. The more resonance forms I can draw, the more stable something is. And now I'm smiling real good because Dr. White loves, and this is called the enolate anion. And my PhD thesis dealt with, and most even organic chemists will not understand what I'm about to say. My PhD thesis dealt with the use of kinetically favored cross-conjugated enolate anions. I told you I was an authority. And if I look at the clock, oh, we still have time. So this means that you can easily remove a hydrogen from the alpha carbon with a base because it's acidic. And remember, in case you forgot, acid, base, proton transfer, and guess what? With a base, you can pull off the proton, which in this case is one of the hydrogens on the alpha carbon to form an enolate anion. When you do enolate anions, you can do something very special. But I'm going to be cruel, and we're just about there. Let's take a break. Come back in about 5 minutes. Looks like we're just at that, almost at 2:45. Come back at 2:50, about 5.5 minutes. I can give you an extra 30 seconds, and I'll see you in 5. We'll continue with this and finish the chapter, start a new chapter, do our lab, and then you're gone. I don't know about gone, but you're done for today. I'll be back in 5. Ooh, I nailed it, 2:50. Come back, please. Time to get going. All right, I was talking about the enolate anion. And the enolate anion has a carbon with a negative charge and a sodium or some cation associated with it. And it's reactive. It wants to get rid of that negative charge in the worst way. And how does that do that? With the following reaction. And that's the Aldol condensation. Oop, didn't want to do that. And here I have one way of showing that, and I'm going to show it another way on the whiteboard. And here you take a base, and usually also have a solvent, like water will work, ethanol will work, an alcohol, and you react an aldehyde with itself. And you can do a ketone, but for this class, it'll be easier for you if we just stick to aldehydes. And it's time for a special gift from Dr. White. So let's look at the aldol condensation and also condensed condensation. You bring two things together, and I'll explain how they got the name aldol. So let's look at this. For this class, and you can do this with a ketone too, but for this class, to make your life easier, one, I'll stick to an aldehyde. And two, to make your life even better and easier, I'll write on the test two of the same aldehyde. In real life, an organic chemist who don't balance things would just write the aldehyde and then react it, and I'll stick to this base, sodium hydroxide, and water. That forms the enolate anion, this carbon, and like a Grignard, the minus charge attacks the other carbonyl carbon of the other aldehyde and forms something very special, very rare, a carbon-carbon single bond. And that's the amazing thing of enolate anions. You can form carbon-carbon single bonds. Now, if you look at the molecule I just made, it's got an alcohol, OL ending, and it's got an aldehyde, ALD. And that's how they got the name Aldol. And let's have some fun. Oh, one other gift. Oh, I'm in a gift-giving day today. I will never on a test put a synthesis problem for the aldol condensation reaction. That's not fair. So let's look at the following. Give the organic product or product for the following reaction. Now, sodium hydroxide is a base, and it will form the enolate anion here by removing one hydrogen. And that carbon, the alpha carbon, will now, as an enolate, attach the other carbonyl. And so what's attached to it, oops, I forgot to write the general reaction. Got so excited. Oh, am I happy? You can use other bases. Again, alpha carbon attacks that. What's attached? And you lose one hydrogen there. And you make a carbon-carbon single bond to the other carbonyl carbon. That opens up to an alcohol. What was attached to it, hydrogen and CH2R, is still attached to it. And now, if we look at this, here's my R group. The alpha carbon. Notice I've removed one hydrogen, and this carbon will bond to that carbon. Open it up to an alcohol. And what was attached to it, CH2 cyclopentane ring, is still attached to it. And you've made a very, very complex molecule from a simple molecule reacting with itself. And that's the beauty of enolate anions and the Aldol condensation. And I better share. And by the way, the switch is on for this reaction. This is going fair game on a test, but I'll never put a synthesis problem using this reaction. And the question is, give the organic product or products to the following, 3 points each, your turn. This one's a challenging reaction. So I do have in the practice problems, practice for you. All right, I think everybody's done, so I better get to work. And if we look at this, what's the product or product? Look for what's different, what's not carbon, what's not hydrogen. Just get your attention like that. And we have oxygen double bond to carbon, same here. We've got two of the same aldehyde. Reacting with sodium hydroxide and base, sodium hydroxide, NaOH, water, H2O. Remember, the alpha carbon is acidic. Protons, you remove one, form the enolate anion, which attacks the other carbonyl and opens it up to an alcohol. What was attached to that is still attached to it. And what's our methyl? So I'm going to remove a proton from the alpha carbon, form the enolate anion. That attacks this, bonds to it, but we'd say attacks, opens it up to an alcohol, OH group, was attached to it, is still attached to it, and that's the product. Wow, that was a lot. And that's what makes these reactions with enolate anions impressive, because right here, you made a brand new, very rare carbon-carbon single bond. And notice you started with a molecule with 3 carbons, you ended up with a molecule with 6 carbons, and a lot of functional groups to do stuff with. And that's the beauty, and it is beautiful, of the Alloy condensation. Now you know I'm an organic chemist when I look at this and say, wow, that's beautiful. It is. All right, important announcement. We have just finished everything for the aldehydes and ketones problem set. And keeping with the way I teach, I always finish up a week in advance of the test of new material that will be on the test. That gives you time to practice it, which means that gives you time to do good on, in this case, test number 2. All right, I will be talking about, or what am I saying, talking? I will go through on Monday the ketones and aldehydes problem set. I'll say that again. I'll go through on Monday the ketones and aldehydes problem set. Also on Monday, I'll do my world famous review for next test. In this case, it's test number 2. And then we'll cover new stuff that won't be on test number 2, just like we're going to get into right now, but will be on test number 3 later on down the road. So let's get to the new stuff. And you know what time it is? It's new chapter time, new functional groups. And are you going to be surprised what Dr. White can get into? This new chapter, you'll learn things that when you, oh, is that sour? Pretty sour stuff. We'll also get into stuff you'll never believe I get into. I'm not going to tell you all of it, but I'll get to talk about, are you ready for this? Ketchup, mustard, and pickles, all the good things you put on hot dogs or hamburgers. And also I'll even talk about the relish here we use in Chicago on hot dogs. That is that bright green that glows in the dark. That doesn't glow in the dark, but you know what I'm talking about. You ever had a good Chicago hot dog? And that new chapter, and again, this will be on test 3, not test 2, is carboxylic acids and their derivatives. Now, derivatives means molecules that are derived, made from carboxylic acids. So carboxylic acid, it's a new functional group you don't know about. It contains both a carbonyl group and a hydroxyl group, and the name is carboxylic acid. And the general form of a carboxylic acid, which I will use, and my software didn't put the carbon in, and most likely I'll write it this way or this way. Now, there's other ways we can write it, and you'll see that on Wikipedia and in books and in other classes, which I will get to later on, either like this, what Dr. White never uses, or like this, which I do use. And notice you've got a carbon right here with 2 oxygens and a hydrogen on the one of the oxygens, which is the same as that carbon or this carbon. And this is a carboxylic acid. And one of the things I'm going to get into, you wouldn't even believe he's talking about that. OMG. Now, how do you name a carboxylic acid? Well, first of all, let me put one on the whiteboard. And the first thing you have to know is what functional group is this? And you look for something different. Ooh, an oxygen double bond to carbon, and that same carbon has a hydroxyl group. That's a carboxylic acid. In this case, this is R right here. But how do you name that? Well, good question. And how do you name it is you find the longest chain that has the carbonyl carbon, carbon double bond to oxygen, carbonyl group, group can be in more than one functional group. Now you find the longest chain, which includes the carbonyl carbon of the carboxylic acid. Name that as an alkane. Now, once you get the alkane name, drop the E at the end of NANE and replace it with the letters OIC and the word acid. Again, find the longest chain with the carbonyl carbon, name it as an alkane, causes a carboxylic acid, drop the E at the end of ANE, add OIC in the word acid. Now, like aldehydes, carbonyl carbon of a carboxylic acid is always number 1 because it rocks. Yeah. And you name that as number 1, and the rest of the stuff you name just like you did alkyl groups before. So let's take a look at how to do this. Now here's our carbonyl carbon right here. What's the longest chain? 1, 2, 3, 4, 5. That would be pentane, was an alkane, but no, it's a carboxylic acid. You drop the E, add OIC, and the word acid, and that's pentanoic acid. Everybody knows this is number 1, therefore you don't put a number like ketones or alcohols in front, and that's the name of that, pentanoic acid. I should warn you, I've worked in this area in the chemical industry, and Dr. White knows his carboxylic acids. Now, what if there's an alkyl group? And I'll do this one. You look and say, what's the IUPAC name for this molecule? You look there and say, what's different? Ooh, carbonyl, carbon double bond to oxygen, and to that same carbon, you have a hydroxyl group, OH. And what is that? That's a carboxylic acid. And how do we name that? We find the longest chain. Well, there's 1, 2, 3, or there's 1, 2, 3, 4. And I hope you all agree 4 is greater than 3. That's butane. But you have a carboxylic acid, you drop the E, add OIC, and the word acid, butanoic acid. Are we done? Well, as soon as I say butanoic acid, that's all smokable. Oh, look what's left over. It's your old friend, the methyl group, and it's on carbon 2. So just like any other alkyl group, you have 2-methyl-butanoic acid. And that's how you do it. So I better let you try one. What would be the IUPAC name for that molecule? All right, I think everybody's done. Let's take a look at this. Oh, wait, I'll give you another 8.9 seconds. 8.2, 8.6, 8.9. And if we look at this molecule, how do we know what to name it? Well, look for what's different. Oh, I've got a carbonyl, carbon double bond to oxygen. It's that same carbon. I have a hydroxyl group and carbons attached, and this is a carboxylic acid. And how do you name it? Find the longest chain, 1, 2, 3, and that's propane. Drop the E, add OIC, and the word acid. And we're done. That's called propanoic acid. Oh, let's do one more. And why don't you try that one? What would be the IUPAC name of the following molecule? 3 points each. I should tell you, this is a very nasty, evil molecule because it caused about 6 weeks of grief in my life because it was impurity in the starting material. Once I identified it was in there and it shouldn't have been, I no longer had that grief in my life. But to this day, evil. Didn't know molecules can be evil and nasty. They can. All right, looks like everybody's done. Let's proceed. What's different? Ooh, carbonyl with a hydroxyl group and carbons. And that's a carboxylic acid. And if we look at this, what's the longest chain that contains the carbonyl carbon, carbon double bond to oxygen? Well, I can do 1, 2, 3, 4, or I can do 1. Remember, the carbonyl carbon is always 1 in a carboxylic acid. 2, 3, 4, 5, 6. I hope you agree 6 is greater than 4. That's hexane for an alkane, but it's a carboxylic acid. Drop the E, add OIC, and the word acid, hexanoic acid. And we have here an ethyl group on carbon 2, and that's 2-ethyl hexanoic acid, which gave me a lot of grief in my life for a couple of weeks. It was not a fun time until I isolated that as an impurity. Now, there's a common name that became the IUPAC name. When in a carboxylic acid, R is a benzene ring. This thing 6 months ago, you would know what a benzene ring was. See how much you've learned? Aren't you proud? And this is called benzoic acid. How it got that name, don't know. I sort of see, but it's benzoic acid. And that's both the common and the IUPAC name. And if I look at the clock, which I just did, it's time for a lab. Don't forget the lab we did last week is due today. Don't forget to upload your labs because they're points toward your final grade. Easy points because I'm not a tough grader on labs. I shouldn't have said that. But let's talk about today's lab. And what does today's lab deal with? Alcohols. And thumbs up, people. Everybody see Chem 170 alcohols lab on your screen? Thank you, everybody. All right. Now, because alcohols are flammable, if we were face-to-face, you see where don't use any matches. In our lab, we never use Bunsen burners, lighters, or matches, period. All right, now I would tell you about the different ways. Now, the first thing, when we're talking about an alcohol, what is the structure of an alcohol? Now, it turns out alcohols like water, when you have the oxygen being more electronegative than the hydrogen, there's a slight positive charge on the hydrogen and a slight negative charge on oxygen. And if we look at water, the same thing exists. And because of what's called the hydrogen bond, there can be a slight attraction between the water and alcohol. And that makes certain alcohols more soluble in water. Now, what you have to consider is the molecular weight. How big is R? And this part of the lab, you'll find out how big it is. And what you would do if we were face-to-face is in a small, clean test tube, you add some deionized water to fill it about 1/3, add about 5 to 10 drops of the alcohol, and then you mix it. And as I don't know if I taught you this, I'm trying to find something good to, let's assume this a test tube. Never ever shake a test tube like this. Hold it firmly. I think we've already done this. And go 1, 2, 3, 4. Don't tickle it. Really hit it. That will mix it. We also have the Vibral Mixers That's a plate that vibrates super fast. Hold the test tube, put it down, and when you push on there, it gets it vibrating and it mixes it. And then what you do is you let it sit for a minute or 30 seconds and see is it the same throughout or are there two layers? And if it's the same throughout, the alcohol is soluble. And here are the alcohols you would have used. And for this table, notice in red, underneath the name, please draw the structures for the alcohols in that table. And if you were in the lab, we would find out ethylene glycol, isopropyl alcohol, also known as 2-propanol, and tert-butyl alcohol are soluble. 2-hexanol and 1-octanol are not. They're insoluble. And then I'd say we have a waste bottle. This doesn't go down this sink. We're trying to keep our environment safe and sound. That's why we don't dump things down the sink. Now, the second one, I would have different alcohols for you to smell. And the philosophy, when I inherited this class years ago, and the labs were, well, saying they're awful is being too nice. They're beyond awful. And I created my own, and I wanted to give you experience of alcohols. And here with odor, if you put a little on the paper, take it and go like this and smell it, and put down what you smell. And here's something usually students use, put down there. And this is giving you an experience of alcohols. Now, the next one is oxidation of alcohols. And this is reacting alcohols with potassium dichromate. And I have to teach you a new reaction. Well, you've learned this with another reagent, but let's look at the following. And you learned there are different types of alcohols. This is a primary alcohol. And if I react it with sodium dichromate in solution, and this is a orange, red, depending on what concentration, how red it looks, this gets oxidized like you learned to make an aldehyde. This gets reduced to chromium +3 compounds. And depending on the concentration, this is either green or a blue-green color, almost a turquoise. And that tells you there, if it's color changed to this, there's an alcohol. And the same thing happens with a secondary alcohol, which you can oxidize. And if you see a color change, that tells you you had a primary or secondary alcohol. Now, if you had a tertiary alcohol, tertiary alcohols cannot be oxidized, and you get no reaction and no color change. So this is a way of determining, do you have a tertiary alcohol or a primary or secondary alcohol? And before we had the modern instrumentation we now have, this was an important visual determination of the type of alcohol you had. Now here, to do the reaction, if we were in the lab, we would take a small test tube, put about 5-10 drops of the alcohol, add about 10 drops of the acidic, and you put some acid in there to help it go quicker as a catalyst. Dilute acidic potassium dichromate, you mix it, let it sit for a while, and you observe what it looks like. And then you repeat that for, and this really should, A and B, steps A and B, for the other alcohols. And because it's highly acidic, wear eye protection, which we always do. And I tell students, put on gloves. And here, if we have the different alcohols, you see this is blue-green, this alcohol, ethylene glycol. Isopropyl alcohol is blue-green, and the 2-methyl-2-propanol is orange-red. And that's 2-hexanol, 1-octanol also goes blue or blue-green. It's a mixture. Depending on concentration, it looks bluish or blue-green, sometimes even green. All right, now the final part is, this is one I do a demonstration because I don't trust students working with sodium metal. I have, you haven't had that experience. And here, we're going to talk about the reaction of alcohols with sodium metal. If you take any alcohol, primary, secondary, or tertiary, and this is one of the rare times I'm going to balance the chemical equation, because students get upset when I don't for this, and I don't need upset students. Take an alcohol reaction with sodium metal, you get a nice reaction, and you form the alkoxide, plus hydrogen gas, which is given off as a gas. That means gas, which means you would see bubbles. And one of the things that you don't know, but I'll teach you, is alkoxides are very basic, very stronger than other bases. And what does that mean? Remember, pH scale. At 7, you have what's called neutral pH. Below 7 here is called acidic. And above 7 is called basic. And you should have learned that in general chemistry. If not, I just did a review. So if I take an alcohol and react with sodium and measure the pH of the product, if I'm telling you the truth, it should be very basic. Basic means greater than 7. The closer to 14, the stronger the base you're dealing with. And what I do in the lab, I take some water and isopropanol and measure the pH with pH paper. I actually, in the lab, I'd show it to a student. I'd say, all right, this is what I think the pH is. And you would look at it. By the way, thumbs up, people. How many of you have ever worked with pH paper? Not many. But anyways, it just a few of you are coming in now, but it changes color. And I think I have a link in here. Do I have a video? Nope, I don't. But anyways, you can find it on YouTube. Now, when we take and first put 2-propanol, otherwise known as isopropyl alcohol, and sodium, you would see, and I don't have that down here, you would see bubbles. And when I take some of that and put it in water and measure the pH, it's now 13. And that's the demonstration. And I show everybody the reaction. I do this in a beaker, and you'd see all the bubbles form. It's fun. And if you look at the end, there's questions for you to do. And notice right here, please just use your experimental results to justify your answers. I don't need a whole constitution, like 20 pages. Most of these you can do in 1 or 2 sentences with the justification 2 or 3 total. And with that, normally like I said, we're just about caught up. And in the future week, maybe not next week, but after that, we'll end earlier on a Wednesday, because this would be the time after I talk, you'd go into the lab and get data, but I'm giving it to you. With that, remember, next Monday, I will be doing the aldehydes and ketones problem set. Next Monday, I will do my world famous review for next test number 2, and we'll do new stuff too. A week from today, looking at my calendar up here, the 9th, we will have test number 2. Scratch my hands here when I was working in the house. It happens. I forgot to put gloves on. Bad, Dr. White. Leather gloves. I should have, but I didn't. But anyways, we'll have test number 2 between now and Saturday. I'll put out an announcement, the exact points breakdown, how many problems, how many pages, and like test number 1, if you have done the practice problems and study a little, you'll be in good shape to do good on test number 2. And with that, I'm done. And I'm going to say, Gang gesund. I haven't done this with my left hand before. I'm ambidextrous, so I can do that. Gang gesund. I stole that from Granny and the Beverly Hillbillies. Bye now. I'll see you next Monday, unless you come to my office hours. Bye.